So the topic of today's lecture is cholinesterase or inhibiting and cholinergic receptor activating drugs. So these drugs will promote the activation of the parasympathetic nervous system, and they have a limited clinical uh, value. However, some of them are used in ophthalmology and urology. And the cholinergic activating and cholinergic inhibiting drugs can be classified to uh, the several types, depending on the action on the receptors and on the type of the receptor. And the parasympathetic nervous system is activated by the muscarinic muscarine, and by activating the muscarinic receptors. And application of the muscarine to the ganglia and to the autonomic effector tissue, that is smooth muscles, heart, and exocrine glands, showed that the parasympathetic action of the muscarine occurred through an action on receptor on effector cells, not on ganglia. The effects of acetylcholine itself and of the cholinergic drugs at autonomic neuroeffector junctions are called parasympathomimetic effects, and they are mediated by the muscarinic receptors. So, and another alkaloid, nicotine, stimulated ganglia mostly, and also the skeletal muscle neuromuscular junctions, but not the autonomic effector cells. The ganglion and skeletal muscle receptors were therefore labeled nicotinic, so nicotinic receptors. And when the acetylcholine was identified and it was identified that both muscarinic and nicotinic receptors are activated by acetylcholine. Cholinereceptors are a member of the either G-protein linked or ion channel families on the basis of the transmembrane signal mechanism. So the muscarinic are G-protein coupled and nicotinic are ion channels. Muscarinic receptors contain 7 transmembrane domains whose third cytoplasmic loop is coupled to G-protein that function as the transducers. This receptor regulate the production of intracellular second messages and modulate certain ion channels via the G-protein. The agonist selectivity is determined by the subtypes of muscarinic receptors and G-proteins that are present in the given cell. So the muscarinic receptors are located on plasma membranes of cells in the central nervous system in organs innervated by the parasympathetic nerves, as well as on some tissues that are not innervated by these nerves, for example, endothelial cells, and on those tissues innervated by postganglionic sympathetic cholinergic nerves. Nicotinic receptors are part of a transmembrane polypeptides whose subunits form carbon-selective ion channels. These receptors are located on plasma membranes of postganglionic cells in all autonomic ganglia and of muscles innervated by somatic motor fibers and of some central nervous system neurons. So direct acting cholinergic drugs bind to and activate muscarinic or nicotinic receptors. Indirect acting agents produce their primary effects by inhibiting acetylcholine esterase, and the indirect acting drugs increase the endogenous acetylcholine concentration, and that leads to the activation of the receptors, muscarinic and or nicotinic, depending on the neuromuscular junction or the ganglia. The excess acetylcholine in turn stimulates choline receptors to evoke increased responses. These drugs act primarily where acetylcholine is physiologically released and are thus amplifiers of endogenous acetylcholine. Some cholinesterase inhibitors also inhibit butyrylcholinesterase, that is pseudocholinesterase. However, inhibition of butyrylcholinesterase plays little role in the action of indirect acting cholinergic drugs because this enzyme is not important in the physiological termination of synaptic acetylcholine action. The acetylcholine has this kind of structure, so this is acetyl and this is a choline, and the based on the chemical structure, the direct acting cholinergic drugs can be divided on esters of choline and alkaloids. So alkaloids actually are muscarine and nicotine, and esters are acetylcholine, metacholine, carbocholine, and the beta-nicotine. So these drugs have effects on both receptors. Acetylcholine is typical, and few of them are highly selective for muscarinic, like the beta-nicotine and metacholine, or for the nicotinic receptor like nicotine. However, none of them clinically useful because they are non-selective towards the subtypes of the receptors. 4 imported choline esters have been studied extensively, and their permanently charged quaternary ammonium group. So this is a quaternary ammonium group because it has 4 bonds. So this is highly polar molecule, and This makes them insoluble in lipids. Many naturally occurring and synthetic cholinomimetic drugs that are not choline esters have been identified. A few of these are pilocarpine and lobeline. The muscarinic receptor is stereoselective, and for example, bethanechol is more so as bethanechol is more potent than the right R bethanechol. Choline esters are poorly absorbed and poorly distributed into the central nervous system because they are hydrophilic due to the ammonium, quaternary ammonium that is charged. Although all are hydrolyzed in the gastrointestinal tract, they differ markedly in their susceptibility to hydrolysis by cholinesterase. Acetylcholine is very rapidly hydrolyzed, and large amounts must be infused intravenously to achieve concentration sufficient to provide detectable effects. That is why acetylcholine is not used in clinics. Methacholine is more resistant to hydrolysis, and the carbamic acid esters carbachol and bethanechol, because of this carbamide group, are more resistant, and they have longer duration of action. The beta methyl group of the bethanechol and of the methacholine reduces the potency to the nicotinic and give a muscarinic selectivity. So methacholine is called because in beta position, so this is alpha carbon, this is beta carbon, and on beta carbon methacholine has a methyl group, and bethanechol also has a beta methyl group in so structure is common, but the difference in betacholline, it has a carbamic acid group, so it's carbamyl derivative, not acetyl derivative like methylcholine. The tertiary natural cholinomimetic alkaloids, pilocarpine and lobeline, as well as the nicotine and muscarine, are well absorbed from most sites of administration. Nicotine is a liquid, is sufficiently lipid soluble to be absorbed across the skin, and they now produce the transmembrane nicotine plasters to help in smoking cessation. And muscarine is a quaternary amine, is less completely absorbed from the GI, but is still toxic when ingested. So because you can be poisoned by eating mushrooms. And lobeline is a plant derivative similar to the nicotine. I think you studied it on pharmacognosy. And the amines are excreted chiefly by the kidneys, acidification of urine accelerates clearance of the tertiary amines. So the mechanism of action. So mechanism of action is based on the action on the receptors, because acetylcholine is released by the parasympathetic nerves and activates muscarinic receptors on effector cells, and this is direct action. And then also it acts on the muscarinic receptors on nerve terminals to inhibit the release of the neurotransmitter. By this mechanism, acetylcholine release and circulating muscarinic agonists indirectly alter organ function by modulating the effects of the parasympathetic and sympathetic nerves. Then the most of the direct organ system effects of muscarinic cholineceptor stimulations are readily predicted from knowledge of the effects of the parasympathetic nerve stimulation, and also by the distribution of muscarinic receptors. So we already studied them on general pharmacology, and mostly they act on the autonomic ganglia and skeletal muscle motor end plate with the nicotinic, and to the autonomic systems with the muscarinic. So muscarinic agonists act on the eye when instilled to the conjunctival sac. They cause contraction of the smooth muscles of the iris sphincter that leads to the miosis, and also they stimulate the ciliary muscle, resulting in accommodation fixation. As a result, the iris is pulled away from the angle of the anterior chamber, and the trabecular meshwork at the base of the ciliary muscle is opened. Both effects facilitate aqueous humor outflow into the canal of Schlemm, which drains the anterior chamber. So the primary cardiovascular effects of muscarinic agonists are reduction in peripheral vascular resistance and changes in heart rate. The direct effects listed are modified by important homeostatic reflexes, and intravenous infusion is minimally effective. Doses that cause vasodilation are very high, resulting in reduction in blood pressure. And they are also accompanied by a reflex increase in heart rate, and larger doses of acetylcholine reduces bradycardia and decreases atrioventricular node conduction velocity in addition to hypotension. The direct cardiac action of muscarinic stimulants include the increase in potassium current and a decrease in the slow inward calcium current, and reduction in the hyperpolarization activated current that underlines the diastolic depolarization. All these actions are mediated by M2 subtype of receptors and contribute to slowing the pacemaker rate. So the muscarinic stimulants contract the smooth muscle of the bronchial tree. In addition, the glands of the tracheobronchial mucosa are stimulated to secrete. This combination of effects can occasionally cause symptoms, especially in individuals with asthma. The bronchoconstriction caused by muscarinic agonist is eliminated in knockout animals in which the M3 subtype receptor has been mutated. Administration of muscarinic agonists as in parasympathetic nervous system stimulation increases the secretory and motor activity of the gut. The salivary and gastric glands are strongly stimulated. The pancreas and small intestinal glands are stimulated less so. Peristaltic activity is increased throughout the gut and most sphincters are relaxed. Stimulation of contraction in these organ systems involves depolarization of the smooth muscle cell membrane and increased gastrin influx. Muscarinic agonists do not cause contraction of the ileum in mutant mice lacking M2 and M3 receptors. The M3 receptor is required for direct activation of smooth muscle contraction, whereas the M2 receptor reduces cyclic adenosine monophosphate formation and relaxation caused by sympathomimetic drugs. Muscarinic agonists stimulate the detrusor muscle and relax the trigone and sphincter muscle of the bladder, thus promoting voiding. The functions of M2 and M3 receptors in the urinary bladder appears to be the same as in intestinal smooth muscle. The human uterus is not notably sensitive to muscarinic agonists. Muscarinic agonists stimulate the secretion of thermoregulatory sweat, lacrimal, and nasopharyngeal glands. In the central nervous system, there are both muscarinic and nicotinic receptors, the brain being relatively richer in muscarinic cells, and the spinal cord containing a predominantly nicotinic cells. The physiologic roles of these receptors are very complex and we will discuss them later. In peripheral nervous system, autonomic ganglia are an important site of nicotinic synaptic action, and neuromuscular junction is also important for nicotinic receptors, but is different from the autonomic ganglia. So both types respond to acetylcholine and nicotine. The action may vary. So the indirect acting cholinomimetics act on the release or on the released acetylcholine and normally acetylcholine action is terminated by enzymatic hydrolysis of the molecule. Hydrolysis is accomplished by the action of acetylcholinesterase, which is present in high concentrations in cholinergic synapses. The indirect acting cholinomimetics have their primary effect at the active site of this enzyme, although some also have direct actions on nicotinic receptors. The main differences between the members of the group are chemical and pharmacokinetic, and pharmacodynamics is almost identical. So there are three chemical groups of cholinesterase inhibitors. First is simple alkaloids bearing a quaternary ammonium group, for example hydrophonium. So this is a positively charged ammonium. The second is carbamic acid esters of alcohols having quaternary or tertiary ammonium, for example the neostigmine. So neostigmine has a also test tertiary ammonium group. So this is carbamates. The third is organic derivatives of phosphoric acid, like acetylcholine. So we don't have acetylcholine here because they are organophosphates. Anthraphonium, neostigmate, and pyridostigmine are synthetic quaternary ammonium agents used in medicine. Physostigmine is a natural occurring tertiary amine of great lipid solubility that is also used in therapeutics. Carbaryl is a typical of, so carbaryl is here, is a article group of a large group of carbamate insecticides designed for very high lipid solubility, so not used in medicine, but absorption into the insect and distribution to its central nervous system are very rapid, so used as insecticides to kill the mosquito. A few of the estimated organophosphates are shown here. Many of organophosphates are highly lipid-soluble liquids. For example, acetylcholine is a acetylcholine derivative, and it has a long duration of action, but is more stable in aqueous solutions. And also the Zoman is an extremely potent nerve gas. Zoman is actually used during the Vietnam War. And parathione and malathione are thiophosphate prodrugs that are inactivate and they are converted to the phosphate derivatives in animals and plants and are used as insecticides, so the same as the carbamide. Absorption of the quaternary carbamides from the conjunctiva, skin, gut, and lungs is predictably poor. So since the permanent change renders from relatively insoluble in lipids, thus much larger doses are required for oral administration than for parenteral injection. Distribution into the central nervous system is negligible. Physostigmine is well absorbed from the oocyte and can be used topically in the eye. It is distributed in the central nervous system and is more toxic than the more polar quaternary carbamides. So physostigmine has no quaternary ammonium, so that is why it's distributed faster. So here is carbamide, nitrogen is carbamide, and here two nitrogens are inside the ring, so that is why and the rings are fused, and also these nitrogens are covered are blocked by the methyl group. So the carbamides are relatively stable in aqueous solution but can be metabolized by non-specific esterases in the body as well as by the cholinesterase. However, the duration of their effect is determined chiefly by the stability of the inhibitor enzyme complex, not by metabolism or excretion. The organophosphate cholinesterase inhibitors are well absorbed from the skin, lung, gut, and conjunctiva, thereby making them dangerous to humans and highly effective as insecticides. They are relatively less stable than the carbamides when dissolved in water and thus have a limited half-life in the environment. Ethiophate is a highly polar and more stable than most of the organophosphates. When prepared in an aqueous solution for ophthalmic use, it retains activity for weeks. The thiophosphate insecticides are quite lipid-soluble and are rapidly absorbed by all roots. They must be activated in the body by conversion to the oxygen analogs, a process that occurs rapidly in both insects and vertebrates. And malathion and a few other organophosphate insecticides are also rapidly metabolized by other pathways to inactive products in birds and mammals, but not in insects. These agents are therefore considered safe enough for sale to the general public. Unfortunately, fish cannot detoxify malathion, and significant numbers of fish have died from the heavy use of this agent on and near waterways. Parathion is not detoxified effectively in vertebrates, thus it is considerably more dangerous than malathion to humans and livestock, and is not available for general public use. All the organophosphates except ethiophate are distributed to all parts of the body, including the central nervous system. Therefore, central nervous system toxicity is an important component of poisoning with these agents. So, I think that is all for today, and thank you for your attention.
Thank you.
And see you next week. Bye bye.
Okay, bye bye.